Welcome to my talk, No Higher Order Effects Without Nonlinearity. I just wanted to take that main message up front so that hopefully everybody is curious now why this should be the case. The answers I will present here are based on a joint paper with Andrew Meller and Renaud Lambiot about multi-body interactions and nonlinear consensus dynamics on networked systems. But why did we even bother thinking about this? Networks have recently become very popular to investigate social dynamics. There's only one problem. Networks fail. There are certain higher order dependencies in the interactions, for example, group or multi-body interactions, which a pairwise network setting simply cannot capture. The question is only, when does this become important for the overall dynamics? In this work, we specifically focus on social dynamics, such as consensus, and introduce a three-body consensus model to investigate the possible higher order effects of these multi-body interactions. Dynamics on conventional networks can be classified as pairwise interaction systems. Agents have local pairwise interactions, and the overall effect of the interactions on each agent is the sum of the pairwise interactions with other agents. In contrast to that, a three-body interaction system takes into account the joint influence of triangle neighbors j and k on node I, described by an interaction function f. Therefore, in contrast to the pairwise case, the interaction between node j and k becomes relevant for the influence on node I. Our main goal in this work is to examine if and under which conditions three-way interaction systems can reveal higher order effects that cannot simply be explained by the pairwise interaction systems operating on the underlying network of the triangle. In sociology, it is well known that the dynamics in a social clique are determined not just by the pairwise relationships of its members, but often by complex mechanisms of peer influence and reinforcement. This is captured by the relatable example of joint parental discipline that we can see here. In A, the link between the parents, which can, for example, model a shared opinion, enables reinforcing dynamics that lead to a stronger influence on the child. This is not captured by the independent pairwise influences in B. Therefore, higher order models, such as the previously introduced three-body interaction model that we call 3CM, additionally account for the effect of the group as a whole. Let us introduce an interaction function that can capture this reinforcing effect. It consists of a linear consensus term and an influence function s of x that captures the higher order influence of the triangle nodes j and k on node I by scaling their pairwise influences by their state difference, modulated by the scalar influence function s of x. Let's assume that s of x is monotonically decreasing now. As we can see in this small example, node P and K therefore reinforce each other, as they have very similar node states. In contrast to that, K and J hinder each other, as they are very distinct. This also models the example of before of joint parental discipline, because parents can support each other in disciplining a child if they have very similar viewpoints, whereas if their opinions conflict, they might hinder each other. If we rewrite the model to relate it to a weighted version of the network Laplacian of the underlying network, we first have to define a weighted adjacency matrix W. The entries Wij account for the higher order effects on node I over edges Ij. The weighted Laplacian is then the matrix representation of the nonlinear dynamics. If s of x is constant, which then gives us linear dynamics again, this operator is not time dependent and reduces to the so-called motive Laplacian for triangle motives, which has been introduced in the literature. We are then basically dealing with rescaled pairwise dynamics. In the nonlinear case, though, even if it seems like a reformulation to a pairwise system, the entries of the weighted Laplacian are then dependent on the node states of the neighboring triangle nodes, which creates the higher order dependencies on the triangle structure. We can conclude that in order to reveal any genuine higher order effects of three-way interactions, which cannot be explained by the underlying scaled pairwise interactions, we must have nonlinear dynamics. This general result of our work underlines that a triangle topology alone does not guarantee that higher order effects will appear, but this also heavily depends on the type of interactions present. Let us now look at possible higher order effects that may emerge from this model. We investigate the possible higher order effects in 3 different scenarios. We first apply a mean field approach to eliminate the topological effects of the distribution of the triangles in the hypergraph. In the second scenario, we then additionally take into account asymmetric topologies by examining 2 connected clusters representing polarized groups. And in the third last scenario, we see joint effects of initialization and topology that result in time-scale separation of the dynamics. Generally, we are interested in if and how a given system reaches consensus, which means that all node states have the same value. This property is conserved on undirected networks. We now investigate in which cases the consensus value is affected by the higher order dynamics in 3-way interaction systems. There, as we can see here, the average state is only conserved if the weighted adjacency matrix that we have derived before is symmetric for all times. This is only generally true for linear dynamics when s of x is constant, which confirms the theoretical result that we derived before, that we're then just dealing with scaled network dynamics. For nonlinear dynamics, though, this symmetry is generally not the case, but depends on initialization, triangle structure, and interaction function. We now want to look at what can happen when those kind of imbalances occur. For this, we first consider a fully connected hypergraph. The displayed condition reminds us when the weighted Laplacian is symmetric, so when the average state is conserved for all times, as we have derived before. In the mean field now, we expect this to happen for an initial node distribution with an average equaling 0.5. Then, as all nodes are connected, the higher order effects balance out initially. And as the system otherwise is symmetric as well, this then expects to hold for all times t. This motivates the assumption that a biased asymmetric initialization, distinct from 0.5, is required for higher order influences on the average state of the system to occur in a mean field setting. The average state then evolves in the dynamical process, and as similar nodes reinforce each other, the shift is enlarged. The numerical simulations confirm that this shift towards the majority in the initial population is present only for the nonlinear reinforcing interactions and not in the linear case, as expected. This reflects how peer pressure can cause opinion drifts in the population, which would not be present in a simple network setting. In the second scenario, we now investigate the influence of asymmetric topologies, in particular of 2 connected clusters that consist of the same number of nodes, and one cluster is initialized with 0 and the other one with 1. The clusters are connected by a set of triangles, and we call a connecting triangle between cluster A and B directed towards cluster B if A contains the inner edge, so the majority of the nodes. Due to the consensus in cluster A, which contains the inner edge, the diffusion on the 2 outer edges of the connecting triangle is accelerated. On the contrary, the influence is inhibited in the opposite direction, as the 2 outer edges damp the diffusion due to the large state difference between the clusters. This leads to directed dynamics between the clusters, even if the system itself is undirected. Therefore, even if the initial average of the system is 0.5, which led to the conservation of the average state in the previous mean field case, the asymmetric connection now leads to one cluster conquering the other. If we define a directedness parameter p, which is the fraction of triangles that are directed towards cluster A, we can observe a shift in the final consensus value from the value of cluster A to the value of cluster B, which we can see in A. This is expected for reinforcing dynamics as the connection is maximally directed towards cluster B for p equal to 0 and towards A for p equal to 1. This also influences the convergence speed, as shown in B. The more directed the connection is, the higher is the acceleration of the dynamics. The simulations also show high standard deviations for values very close to p equal to 0.5. This indicates that the dynamics are very sensitive to even small deviations from a balance in the initial topology that may result from different distributions of the triangles on the network, which can then lead to large differences in the consensus value. To achieve directed dynamics between two clusters, their initial states have to be sufficiently different to accelerate diffusions in one direction or the other. In the previous case of binary initialization, this difference was maximal. We now initialize both clusters uniformly randomly over separate intervals, and we thus observe timescale separations of the dynamics. The clusters are internally fully connected, and therefore the inter-cluster dynamics are generally more inhibited due to the difference of the initial cluster means. As a result, we first observe symmetric dynamics within the clusters towards their specific means, and then asymmetric dynamics between the two clusters. Let me summarize our main results and what you should take away from this presentation. We have introduced a new model for consensus dynamics on three-body hypergraphs, which can be used to show that group interactions reveal higher-order effects that are not captured by pairwise network models. But the most important fact is we find that non-linearity is essential to reveal genuine higher-order group effects. For linear interactions, the dynamics can always be rewritten in terms of a scale network. Moreover, the higher order effects that result from reinforcing group dynamics, such as peer pressure, can lead to interesting shifting phenomena that can only be explained as an interaction of initialization, higher order network topology, and the nonlinear interaction function. Thank you for your attention, and to end this presentation, I would like to thank Andrew Meller and Renaud Lambiot for the great collaboration on this work, and I hope you are as excited about higher order models as I am now. And yeah, please ask all questions that come to your mind.